Yeah, so many thanks for the kind introduction. So actually that's all the story you need to know. So feel free to, no, just kidding, please stay. So the real details are coming now. So it's really great that so many people are actually still here in the room and want to hear something about I'm really caring, and that's OnMetal, the Cloud Native Infrastructure as a Service provider. So, whoops, that was too fast. So as you can see on the first slide, it's actually currently, and that's really a highlight here, currently a joint development effort between T-Systems and SAP. So next time maybe there will be a third or more logos on it, hopefully. So why I'm here and talking about it? So first of all, as I already said, I'm caring about it, but why? So as a cloud architect, in most projects, people approach me and asking me for help to host and operate their cloud native applications, which usually means containerized stuff running in Kubernetes. And so as you can see, I'm also really interested in automation and orchestration, which fits very well with Kubernetes, and OnMetal does the same. So, and I really want to show you because it's amazing. And also to be completely honest about it, so I wanted to go to the ContainerDays and talk about something cool. So I made a deal with my boss, and he said, "Okay, you're allowed to do so, but you also need to talk about something I'm caring about." So there's a slide at the end of the talk. I'm very sorry. So before we dive deeply into the details of OnMetal, I want to start with some background history first, to clarify a few terms, actually the most used ones, and then really explain about OnMetal, architecture, design principles, and features. So as I already said, we were approached by internal as well as external customers asking for help for the containerized stuff running Kubernetes. And both companies, SAP as well as T-Systems, faced multiple challenges. So on T-Systems side, for example, we faced a lot of regulated customers, so finance companies or health care companies, or in the public sector, and they immediately ruled out, after the first sentence asking for help, so they immediately ruled out American or Chinese vendors. That limited the number of options a little bit. So, and SAP, for example, they were also looking for internal offerings and faced quite a lot of licensing fees, which, as good service providers, they passed through to the customers, which they didn't like as much as they did. So we were looking for real alternatives, especially in the open source sector. And unfortunately, all the existing tools were not meeting the expectations of both companies for multiple reasons. Because, as I already said multiple times, we were asked for help regarding cloud native applications. So we didn't need a general purpose infrastructure provider, really a highly specialized one, which ideally can be operated more or less in the same fashion as containers. So we decided to start something on our own. So we were a little bit naive and had the idea, how hard could it be? What could go wrong? And so some things went wrong. So to put it in a nutshell, you could say OnMetal is actually a Kubernetes-driven orchestration of virtualized infrastructure resources. That's already it, but you can be a little bit more specific, especially also more technical. So you could also say OnMetal is just a set of Kubernetes operators and containerized services. So before we now dive deeply into the ideas of OnMetal, I would like to use a few moments to discuss cloud native and Kubernetes-driven in the context of OnMetal, because that made then clear why we do stuff like we do it. So the CNCF actually provides a very nice definition of what is being cloud native, and defining 5 key aspects. The first one is cloud native stuff needs to be scalable. And here this is actually different to the scalability of old traditional stuff. So it's not about scaling up, it's scaling out and in. So distributing load evenly. So that's a fairly known and used concept already for workloads, but for OnMetal we want to have the same behavior. So actually scaling in and out really the used hardware itself, as well as the components managing the hardware. The second thing, or the second aspect is, nevertheless, everything has to be manageable. Of course, it has to be manageable, otherwise you can't use it. But the idea is here, even if you scale out or in, the management efforts don't scale. They are a constant. So it does not matter if you manage a huge setup or a small one. So this is actually usually where people are referring to microservices and immutable infrastructure. And these key aspects, of course, we also use for OnMetal. The third one is that everything needs to be observable. I don't know if you joined the talk, but yesterday there was a nice talk about the paradigm shift in observability. We stick to the old traditional definition of observability. So the system, so in this case OnMetal, and the managed hardware needs to provide status information about itself, right? And ideally in a way that is not new to people or to users. So actually they just know it because they're using it for quite some time already. The fourth aspect is that if you have multiple cloud native components or applications, they need to be loosely coupled. Because if you strictly couple them, or it's not manageable anymore, it's not scalable, especially also using hardware. So here, usually decorative APIs are used. And OnMetal, again, was directly from the start to be designed to follow the same ideas in a way which is already used for years now. And the fifth aspect, very important but often forgotten, it has to be resilient, right? So it's not cloud native if you have just a single component running there and sitting there and then complaining if it gets shut down, migrated, whatever. Resilient means cloud native stuff needs to anticipate failures, either within itself, so if you scale out, one component can fail, or also the infrastructure can fail. But you need to be, or to anticipate it and be prepared for it. You don't need to solve the problem, of course, but you need to be prepared for it. So what means now Kubernetes-driven? And for Kubernetes-driven, we have three key aspects. The first one is standardized orchestration. So if you check the Kubernetes docs, it's clearly mentioned that Kubernetes is orchestrating containers in a generalized way, not caring what these containers are doing or what they are used for. And OnMetal should do the same just for the virtualized infrastructure components. So network, virtual machines, and all these kind of things. The third aspect is the hub and spoke API pattern, which directly refers to the loosely coupled aspect of being cloud native. And the third one is separation of concerns. Again, we all cloud native means that also, well, most people speaking about it having a microservice architecture, and then the microservice components have a well-defined scope. And Kubernetes does the same, right? So you don't have that Kubernetes component, you have actually multiple components with a well-defined scope, and they are mainly categorized into main categories, the so-called control plane, where all the decision-making is happening, and the data plane, which does the black magic for you. And Kubernetes should directly, OnMetal should here not reinvent the wheel. So we have three main domains for managing hardware, right? Networking, storage, and compute. And the OnMetal components are categorized in these three main domains, and then in the idea of having a control plane for the decision making and a data plane which does the black magic. So for compute, for example, the data plane is using the KVM ecosystem, including libvirt and QEMU, for example, for orchestrating VMs without caring what these VMs actually do. They're just getting declarated, and the job will be done for you. The pattern repeats for storage. Here, the data plane is actually using the Ceph technology with the inbuilt Ceph functionalities for providing block and object storage in the same orchestration way as Kubernetes orchestrates containers. And then last but not least, networking. And here the data plane is orchestrating so-called virtual functions for providing virtual network interfaces for VMs, and virtual network instances for providing encapsulated, isolated virtual networks for virtual machines. So, but how are these components, so control plane components, data plane components, are really mapped to an existing data center structure? So usually you start at a certain location, and at that location you have at least one data center building. So depicted here by the big blue box. But at that location you could also have multiple optional data center buildings. So depicted by the transparent boxes. So first key message, it does not matter. So OnMetal should not dictate how the data center looks like. OnMetal should be able to adapt to a given data center architecture. And then in the data center, you have usually subsections. And it starts usually with fire sections. In the fire sections, you have maybe cages. And in the cages, you have racks with the real hardware, routers, switches, and bare metal servers. In the cloud context, we usually call these things a region, a cloud region, or an availability zone. So here the region would reflect the data center building itself at a certain location, while the availability zones would reflect the real fire sections in your data center building. So, but how is now the hardware really used more in the fire section or availability zone to provide the virtualized infrastructure resources you need for your workloads? So here, OnMetal introduces a Kubernetes cluster concept for managing the particular OnMetal components. So here, the first two cluster types are the so-called compute clusters and storage cluster. So as you can see, the storage cluster is actually here in my image stretched over all cloud availability zones, which is up to the guy who deploys OnMetal. It doesn't have to be done like that. It's just an example. But in this way, you can utilize inbuilt Ceph functionalities like data replication, where you have then the hosted data available in each of your cloud availability zones. So the compute clusters, they don't need to be stretched because they represent really a set of bare metal servers in your particular data center subset, or fire section / aka availability zone. However, there are multiple compute clusters depicted here in the image. You have also optional ones in a transparent fashion. Again, the take-home message is OnMetal does not dictate how your data center has to look like. It adapts to your infrastructure. For example, here the multiple compute clusters could reflect different vendors or different hardware features like GPUs, FPGAs, or whatever you have. Important is, if I say cluster, or as the image depicts or indicates, they are real Kubernetes clusters, bare metal Kubernetes clusters, hosting the OnMetal components. So in this case, the compute, control, and data plane, or the storage, control, and data plane. So, but how are these control plane components instructed? So how is the declaration of whatever you need, virtual network, virtual machine, block storage, how is this defined? Of course, it's just a Kubernetes cluster, so you could interact with each cluster individually, but that would be cumbersome, error-prone, and not scalable. So instead, OnMetal defines a so-called user API cluster, which in most cases is a virtual cluster, so it doesn't have any data plane nodes, because it's just an API cluster. It's depicted here outside of the data center building, because it can be hosted wherever you want. Could be in the same cloud region, so in the same data center building, could be a different cloud region, could be actually a different infrastructure provider. Does not matter. What is important here is, even if it's called user API, user in the OnMetal context does not need to be a human. It can be a machine identity, like a Cloud Controller Manager CSI plugin or a machine controller. Moreover, what you can see here is that the arrows between the compute and storage cluster pointing to the user API cluster, which means that the control plane components are not instructed by the API cluster, they fetch the information, as Kubernetes does it, right? So the kubelet is not instructed, it's fetching the information from the API server and then does the magic for you. So, but how is the hardware itself in these subsets, in the fire sections, cloud availability zones managed? Here, the fourth cluster type, the so-called partition cluster, comes into play. It's called partition cluster for a reason, because I already said OnMetal does not dictate what you need to have. OnMetal needs to be flexible enough so that you can use it for your setup. That's why partition, because it's a part of your setup. It's reflecting a subsection. Usually we're referring to it as an availability zone. So in this partition cluster, it's again a bare metal Kubernetes cluster. We have then OnMetal components which really interact with the hardware itself and managing the hardware itself. I will show this in a moment. And then last but not least, we have an unofficial, completely optional type, the so-called region cluster, which is used for hosting centralized stuff you need for the other clusters. Could be DNS, for example, or an image registry. So this is how the OnMetal components are organized or hosted roughly in a given data center. So what I want to depict here is actually now zooming into a particular partition. So because OnMetal orchestrates virtualized infrastructure resources like VMs for you, orchestration means you don't know where things get to be scheduled. So you're just trusting your scheduler, right? You're trusting your infrastructure as a service provider, which means every bare metal server needs to communicate with every other bare metal server, be it in the same partition or in a different partition or even in a different region. That's depicted here. Just to highlight the fact that even if I say OnMetal does not dictate what you need to have, there are some fair assumptions. So if you want orchestration, you need a way that stuff can communicate with each other. And the typical switch architecture is the spine leaf architecture for that. Also, very important, at the top, there's the small in-band network naming. And if there is an in-band network, of course, there's also an out-of-band network. And here the partition cluster comes into play again. As I said, the components hosted in this partition cluster are responsible for managing the hardware itself. So they need a way to connect to the hardware. And here the out-of-band network is used because it's completely isolated from the in-band network, which is used for application workload traffic. So it's really physically isolated, and in case of bare metal servers, the OnMetal components connect to the so-called BMC, the baseboard management controller of bare metal servers. Identifying the server, categorizing it, inventorizing it, and configuring it. I will tell a few more things about that in a moment. Same for switches. So also the OnMetal components connect to the switches using a dedicated management port, configuring the switches, also identifying them, configuring them, inventorizing them, because the switches are part of the partition cluster itself. So the hardware is really managed the Kubernetes way. It's not that somebody needs to manage them directly, needs to go to the console, configure it, or needs to put a USB device into it and flash it all the time. It's configured in a way how you deal or orchestrate manage containers in Kubernetes. Because the black magic or the data plane components are containers managed by Kubernetes. So now the first feature is the so-called auto-discovery feature for hardware, obviously. So imagine so in the old days, you wanted to add new bare metal servers so that you have more compute or storage power. So you instruct your data center operations team, please add a new server, cable it according to the cable plan, bootstrap the server, which usually means plug in a USB stick, flash the server, configuring it accordingly, and then add it to somewhere where it can be used. With OnMetal, they just turn it on, and then they are done. As soon as it turns on, it says hello and gets recognized or identified by the OnMetal components in the partition cluster. And these components do the complete bootstrapping process. As I said, identifying, categorizing, inventorizing, and also, that's very important, configuring the boot order. So it's not booted from disk. It's actually using Pixie boot to get the OS image from an OCI compliant registry and the ignition files from the Pixie service. So, and the use case, and currently it stops here, unfortunately, so there's still some work to be done. The next feature, the next step of this auto-discovery feature is actually auto-scaling for hardware itself. So imagine the bootstrapping process finished, so the server is shutting down again because it's not needed. But now, one of your application clusters wants to schedule a new pod. It's not possible because the cluster is completely full. So what happens usually is that the pod is pending. What people usually do is they have a node autoscaler in place, right? So it detects the pending pod and just instructs the infrastructure provider to provide a new node for the Kubernetes cluster. Okay, but now imagine the compute cluster, so really the bare metal server hosting the VMs, is full as well. So the VM would be stuck. Here now OnMetal, the partition cluster kicks in again and assigns the new bare metal server to the compute cluster, which needs an additional bare metal server, fully automatically. So no human intervention is needed. So it adds this additional cluster. The node autoscaler is happy because the VM is now schedulable and added to your cluster automatically. And then finally the pod is running. But it's not just about hardware, automating hardware, scaling hardware. It's also about pathing through hardware features. For example, confidential computing. And here OnMetal, out of the box, supports the Intel Software Guard Extension technology, in short, Intel SGX, which in a nutshell provides so-called enclaves for securing or providing a secured runtime environment for the application. This includes the code of the application as well as its data. The important take-home message here is that this or confidential computing in general provides a way how the provider can be excluded. I'm working for T-Systems, so we are a service provider, people coming to us asking for help hosting the cloud native applications, which means they only want to throw containers to Kubernetes, nothing more. Everything else is part of our job. But then, of course, they complain, I have sensitive data, so you're not allowed to look. You need to manage my cluster, but you're not allowed to look. That's not going to work. So confidential computing comes to the rescue. So the container is completely encrypted, data in use is completely encrypted. So we can operate the cluster completely as we do SLA-driven, all the kind of things, what service providers do, while the data is completely secure. The take-home message is that it's an inbuilt native feature of OnMetal already. So OnMetal is not just envisioned to be used for internal purposes in your own internal data centers, for your internal workloads. It's also meant for service providers. And also on top, the Intel SGX, there are actually other alternatives than Intel SGX for confidential computing, but Intel SGX offers the narrowest trust boundary. So I don't need to trust the infrastructure, I don't need to trust the virtualization layer, I don't need to trust the VM, because Intel SGX has an inbuilt attestation functionality. Unfortunately, I can't go into much more detail because it would be a talk of its own. Also important is that, as depicted here on the image, so we pass through Intel SGX capabilities to the VM using QEMU, and we're also working on different devices like GPU, FPGAs, and so on in the same way. So far I always spoke about virtualized infrastructure resources, and that's completely true. That's the scope of OnMetal, orchestrating virtualized infrastructure resources. It's not responsible or capable of orchestrating Kubernetes clustered itself. Why? Because that's actually what customers want at the end of the day, right? The Kubernetes cluster they can deploy their applications to. Because there are so many projects out there which actually doing a pretty good job about providing Kubernetes as a service. One of them is Gartner, also an SAP project. And OnMetal supports Gartner out of the box, or the other way around, Gartner supports OnMetal as an infrastructure as a service provider. So OnMetal provides, of course, the Cloud Controller Manager for Kubernetes clusters, the CSI plugin, machine controller, including the Node Autoscaler support. So whatever you need to host Kubernetes clusters on top of OnMetal. Gartner is supporting it in the way that these components get automatically deployed and configured to your cluster if you define OnMetal as an infrastructure as a service provider. Okay, and now I have to keep my promise. I'm pretty sorry. So the question is OnMetal just theory or running in a lab? And the answer is no. T-Systems already has a commercial product. It's called the Open Sovereign Cloud, and it's already running in production. So we run it for 6 months, so it's not that long, you could say, but in these 6 months, we learned real-world experience about OnMetal. So we can really tell you pain points, lessons learned, and the good stuff as well, of course. And I promise to say that. So this is the first platform or complete cloud stack, actually, which is Gematik certified. Gematik is the German regulation agency for digital medicine, I think they are called. So healthcare sector. Yeah, so I'm actually quite fast. Okay, so to sum it up, what's currently going on is still some basic stuff like cloud load balancing, you know, from public hyperscalers. Also the hardware configuration feature I was talking about, but also more fancy things like SmartNIC support. So currently, and I can say a few more things about it. So currently, the data plane of the networking domain is using or creating virtual functions for providing virtual network interface interfaces for your VMs, and the main part is currently done really on the operating system of the bare metal server. And we want to shift that to SmartNIC so that the or the entire compute and RAM power of your bare metal server can be used for computing stuff or providing VMs. Also, default storage encryption is currently work in progress, and very important, open source. As I said at the very beginning, currently there are only just 2 logos on the slide. Hopefully in the future there are more, because OnMetal will be completely open source. So will be means there are some components are already open source, some are not, because open sourcing is actually hard work. I was not aware of that. So contributing is hard work as well, but really starting an open source project from scratch is harder than you think. It's not just a public GitHub repository. So of course, that's not the end of the story. There's more. And my 2 favorites are actually the so-called privacy classes. So far, I spoke always about VMs, and VMs has to be hosted on bare metal servers. And I said, so OnMetal is taking care of orchestrating these VMs for you, so you don't know where they're running, and you don't need to know. The point is, especially from the point of view of a service provider, that can be an issue. So if there are potential side channel attacks available or just identified, discovered, whatever, maybe the VMs of customer 1 should not run next to the VMs of customer 2 on the same hardware. So with privacy levels, as an end user, you can define if your VMs are allowed to run on shared hardware, could be a different internal team, could be another customer of a service provider, or as soon as one of your VMs is scheduled to a particular bare metal server, this bare metal server belongs to you and only to you. Of course, that's more expensive, but you have more privacy as usual, so it's a trade-off. The second key feature I'm really liking is the bare metal machine type. So far I said OnMetal orchestrates virtualized infrastructure resources. That's completely true currently, but the plan is actually that you get also bare metal resources, the real bare metal server. So if you want, you can request a handful of VMs for hosting the control plane of your Kubernetes cluster, for example, or some other control plane components, and then bare metal servers for the heavy jobs. So one of the use cases here, for example, could be that you want to do ML or in Kubernetes using a framework like Kubeflow, for example. So as I said, the Kubernetes control plane as well as the Kubeflow control plane is running on VMs because they're cheap and small, because they don't need so much compute power. But the heavy jobs, the real jobs, they are scheduled to bare metal servers. And you can include this with autoscaling actually, or combine. So which means you define the machine type group or bare metal servers for your jobs, but the default number of instances is 0. So the node autoscaler kicks in immediately as you schedule a job. It provides the bare metal server for you, the job is executed, and as soon as it's finished, the bare metal server will be removed again and also shut it down. That's very important. So whatever OnMetal does not need, it is shutting it down. So you actually also not just save money, you save also energy. Right? So there were quite a lot of talks about sustainability. So OnMetal, I wouldn't say sustainability is a key aspect of OnMetal, but it's fitting the bill pretty good out of the box. So we also have other things planned, for example, also security groups where you can then have basic filtering regarding network packages, and also IPv6 for the overlay network for VMs. Currently, we only support IPv4, but of course, it's obvious IPv6 is the technology which we need to support. The autoscaling for storage and compute clusters I already discussed, so I think that's fine and we can skip it. So of course, so I'm not alone here. Unfortunately, we needed to cut Sebastian's part because during our dry runs, we were using more or less 40 to 45 minutes. So that's why I'm here alone at stage. But Sebastian is with me, so please approach us, ask whatever you want. We love to answer questions. Really, it's not just a joke. We love to discuss stuff. And with that being said, thanks for your attention.
Well, it's excellent that you like answering questions because we have some.
Cool.
Surprise. So there's a lot of, we heard you about this project. What about this project? So what about the Tinkerbell project?
What is the Tinkerbell project?
Tinkerbell.
Tinkerbell.
You know, like Peter Pan, but then Tinkerbell.
To be honest, this project I don't know. It's a little bit embarrassing, but so I mean the ecosystem around Kubernetes is so high, and even if I claimed I'm really interested in it, which is true by the way, but I can't check out every project itself, so I can't tell you what are the differences and similarities. I'm pretty sorry.
Oh, good. All right. So then there is the other. What about what is that? Mobility as a service, I'm guessing. The other thing that I could guess is malware as a service, but I don't think we're talking about that one.
Yes and no. So as I said, so we evaluated existing open source projects before we actually started the development. It turned out that nothing was really fitting our ideas how infrastructure should be orchestrated the Kubernetes way. So as I said, all the components running in Kubernetes itself can be managed the traditional way how containers are managed in Kubernetes using GitHub tools, for example, like Flux or whatsoever. And also, the idea is that hardware is scaled automatically, and that is also true for storage. So in Kubernetes, you have highly dynamic environments, so pods requesting storage, for example, and with all these other tools, also like Mars, there are certain manual steps needed to provide everything. So you cannot fully automate it. Of course, you can write scripts, but if you start to write scripts for these existing tools, you can potentially also, if you have the manpower and the will to do so, you can write your own operators. And if you start to write your own operators, then you're actually pretty close to OnMetal.
All right, let's do one more, and then people can find you at the break.
Sure.
We have a little break coming up. What was the motivation for building the VM orchestration yourself instead of using, for instance, OpenStack?
Yeah, so I expected that one, to be honest. More or less the same answer as the previous one. Or again, so we really want to have it the Kubernetes way. So because also right now at T-Systems, for example, we have one operations team for the entire stack, because the entire stack is just Kubernetes. So even bare metal is managed the Kubernetes way. So if your operations team can manage Kubernetes, they can manage the entire stack, so the entire open source cloud. So there are no differences. So we actually also have another team in T-Systems, which is providing the so-called Open Telecom Cloud based on OpenStack. And they are much bigger, really much bigger than us, and they have quite a lot of stuff to do to manage OpenStack. So it takes much more efforts to manage OpenStack than OnMetal, actually. Also, you need to learn different tooling, because you can't use most of the Kubernetes stuff natively for OpenStack, even if you run it in Kubernetes itself. But if you run OpenStack in Kubernetes, you're, again, pretty close to OnMetal.